You start a coding session with a vanilla AI agent, prompt it to build a feature, and watch the terminal fly. It feels frictionless, right up until you hit an invisible wall. That wall is the context window. Every language model has a finite working memory, and during an active development session, that space gets consumed rapidly. The agent reads a file, writes a bug, reads the file again, and finally fixes the bug. The issue is that all those failed attempts and redundant file reads do not disappear. They are permanently stored in the active memory of your session, polluting the context. Once that memory bloats past a specific threshold, performance degrades. Token costs scale exponentially with every subsequent prompt, and the model begins to forget the exact architectural instructions you gave it an hour ago. Trying to fix this by typing longer, more specific prompts into the chat interface is a failing strategy. The problem is structural. This structural flaw is exactly what the Everything Claude Code framework was built to solve. It is an open-source orchestration plugin that won the Anthropic hackathon, refined over 10 months of daily production use. Rather than relying on a linear chat interface, this framework dismantles the standard environment. It replaces basic chat interactions with dynamic system prompts, isolated subagents, and continuous learning loops. Scaling AI-driven development requires abandoning prompt engineering. To get predictable code, you have to engineer the environment itself. In a standard Claude Code workflow, the agent attempts to follow your project rules by using tool calls to read a markdown file every time you open a session. Calling tools inside the active conversation burns through context, polluting working memory. The framework bypasses this chat loop using command line flags, locking the token counter. It injects project rules directly into the system prompt layer, planting data into the agent's core instructions beforehand. This is critical because of how large language models prioritize information. Instructions residing in the system prompt inherently outrank the context of user messages and tool outputs. If you have non-negotiable coding standards, they must live at this highest level of the hierarchy to ensure absolute compliance from the model. By dynamically injecting these rules upfront, you secure your project constraints at zero recurring token cost, keeping the active window clean for development. Even with a clean start, asking one monolithic session to plan architecture, write code, and run tests creates cognitive and financial chaos. To prevent this, the framework utilizes a roster of 12 specialized subagents, establishing a routing system that breaks work by domain. When a complex request enters, the orchestration layer splits the work. High-level reasoning is routed to the planner node to generate an architectural blueprint. The planner passes this to the coder node. The coder writes the files and returns only a tight summary back. The crucial mechanic here is isolation. Every subagent operates within its own completely separate context window. They do not share chat histories. They execute their specific assignment and then return only their final synthesized output to the parent session. By stripping away the messy intermediate steps, the failed compile attempts, and the raw file reads, the primary project context remains pristine. This modular subagent orchestration keeps the model highly focused on specific deliverables while simultaneously driving down your token economics. But even with perfect delegation, there is a bottleneck: spending time in tokens correcting the agent for making the exact same mistake it made yesterday. Standard AI agents are stateless. Every time you open a new terminal, the agent resets. It has no memory of the architectural preferences or workarounds you taught it in previous sessions. The framework solves this amnesia through a continuous learning loop. You trigger this manually using a specific command, /learn. By typing /learn, the system targets a specific correction. It extracts this behavioral pattern from the conversation, bypassing the active chat history, and routes it into a dedicated local directory. The framework saves this knowledge as a permanent instinct. Whenever you boot up a subsequent coding session, the orchestration layer automatically preloads all of your saved instincts directly into the system prompt. The dynamic shifts entirely. You are no longer repeatedly coaching an assistant. The agent actively evolves its own behavior based on the historical constraints of your specific codebase. By converting passing feedback into permanent instincts, The AI transforms from a repetitive tool into a stateful, compounding asset that does not make the same mistake twice. As this customized environment grows, developers run into a new problem: configuration drift. Keeping rules consistent across Claude Code, Cursor, and Copilot means manually updating multiple sets of instructions. The framework abstracts configuration using the dry adapter pattern, centralizing rules into one format. The system translates this logic on the fly. In Cursor, the adapter maps rules to specific hook events. In Open Code, the same logic translates into distinct skills, without duplicate configuration. Abstracting this logic prevents ecosystem lock-in. Your AI behaves consistently and adheres to your standards, regardless of which IDE you decide to open. This split-screen visualization demonstrates the culmination of the entire orchestration framework, the two-instance kickoff pattern, designed for launching new repositories from scratch. Terminal 1 executes scaffolding subagents to rapidly generate directory structures. Simultaneously, Terminal 2 processes web data and extracts APIs. Being isolated, their outputs merge perfectly into a unified project. This coordination is only possible because dynamically injected system prompts secured the overarching architectural rules for both terminals before they even started. Specialized subagents ensured the raw web data from the research terminal never polluted the context window of the scaffolding terminal, and preloaded instincts guaranteed the freshly generated scaffolding instantly adhered to your personal historical preferences. Relying on a stateless chatbot interface forces the developer to manually coordinate every file and context. Deterministic system-level orchestration automates that burden, turning these models into a reliable multi-agent production pipeline.